Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subject. Today in our class 12th physics playlist, in our electric circuit chapter, we'll study a very simple but very important examination topic, application of potentiometer, and we'll learn how potentiometer compare to EMFs and how one can use potentiometer to determine internal resistance of a cell. And we will also solve some numerical questions which may be asked in our examination. Let's start application of potentiometer. This yellow highlighted section is primary circuit of potentiometer and remaining blue frame part is secondary circuit of potentiometer, and this potentiometer is a voltage measuring instrument. In the primary circuit of potentiometer, AB is a wire of uniform cross section area having R ohm resistance in L meter length, and this circuit is supplied by a source voltage which have a small internal resistance R dash, and a current limiting rheostat is also connected in series to this circuit, and the total resistance in this series circuit of internal resistance of source, rheostat resistance and wire length resistance has total applied voltage V across it, and that circulate a current I in this primary circuit. Now flow of current in wire resistance produce voltage, and L length of wire got R ohm resistance. So resistance per unit length is R by L ohm per meter, denoted by small r. All through the wire length, every unit length have a small voltage drop across it, and this is denoted by small x and known as potential gradient. When this potentiometer is measuring a secondary voltage, then unknown voltage and wire length voltage are balanced, and when the two are equal and opposite in this local loop, there is no current flow circulation in this local loop, and galvanometer shows that by zero center null deflection position, and at the time of balance the voltage drop in unit length of AB wire is called potential gradient, and it is product of primary circuit current denoted by this yellow highlighted relation and per unit length resistance of AB wire. During measurement, a source voltage with a current limiting rheostat resistance is connected to AB wire length of uniform cross section area and establish current in this circuit, and current flow in this AB wire length of uniform cross section area having per unit length resistance small r generate per unit length voltage small x called as potential gradient. Now the voltage which is to be measured is compared with voltage of certain length on AB wire, and when the two voltages, voltage of L length of wire length and measured voltage are equal, then the difference of two in this local loop becomes zero, and in that zero condition this galvanometer won't have any current flow, and this will show a center zero null deflection position, and we call that as balance condition of this potentiometer circuit. And in this balance condition, if primary circuit have potential gradient x in AB wire, then L length of wire will have XL value, and that XL value will become equal to measured EMF E, and this become our balance equations. Now standardization is a process of finding out the value of potential gradient, and for that we use a standard cell of known and fixed value, either Daniel or cadmium cell, and that known EMF is balanced on certain wire length, and the ratio of standard voltage and balance length gives us voltage coming per unit length on AB wire, and the ratio of standard EMF and balance length will give us the value of potential gradient in this AB wire. And once standardization is done, any unknown voltage can be measured just by measurement of corresponding balance length for that voltage on this AB wire. The most common application of potentiometer is measurement of unknown potential, and for that we have to make standardization of potentiometer, and a standard cell is used and corresponding balance length L is obtained, and ratio of standard EMF and balance length will give us potential gradient in this primary circuit of potentiometer. And as potential gradient is product of current and per unit length AB wire resistance, so once standardization is done, to maintain potential gradient constant, the current in primary circuit and per unit length resistance of this AB wire is kept constant. After standardization in this secondary circuit, in place of standard resistance, the unknown voltage which we have to measure is placed, such that the high polarity terminal of this unknown voltage must be connected to high polarity position of AB wire, that is A. Now again balance length L2 is obtained on AB wire corresponding to this unknown voltage, and if potential gradient is as we have standardized, then for for L2 length, the voltage will become XL2, and zero deflection in galvanometer indicates that wire length voltage and unknown voltage are the same. And as we know potential gradient, just by measurement of new balance length will give us unknown EMF, and during this measurement of unknown voltage, this potentiometer circuit won't draw any current from this measured voltage. It acts like an ideal voltmeter of infinite resistance, and without any loading error can measure true EMF. And if there exists some internal resistance in this circuit, even in that condition, in this zero deflection balance measurement, we can measure true value of this unknown EMF. We can compare EMF of two cells without even standardization. As usual, primary circuit is connected to source voltage with current limiting rheostat, and a certain amount of current and potential gradient is established in an AB wire. And now the two voltages which we have to compare are put in additive series combination such that high potential terminal of this combination get connected to high potential terminal of AB wire, that is A, and a corresponding balance length is obtained on AB wire length by suitable positioning of jockey contact. And zero deflection in this galvanometer indicates that L1 length of AB wire section, that is from A to Z, will have potential gradient multiplied by L1 voltage, and this voltage is equal to summation of 2 EMF. Now the lower magnitude of these two is reversed in polarity. So now the two cells are in differential composition and their net voltage is difference of 2 EMF, and again they are balanced on the same primary circuit, and reduced balance length is obtained by movement of jockey contact and zero deflection in this galvanometer, and corresponding to L2 balance length, the voltage of AJ length is now potential gradient multiplied by L2 length, and this become equal to measured voltage E1 minus E2. Now if we add the two equations, the 2 times E1 become potential gradient multiplied by 2 balance length, and when we subtract these two equations we get 2 times the other EMF E2 become equal to potential gradient multiplied by the difference of 2 balance length. And if we take ratio of the two equations, we will get ratio of 2 EMF as sum of balance length of 2 experiment divided by difference of balance length of 2 equations. This example will illustrate how potentiometer is used to compare two resistances. Here in this example, this is primary circuit of potentiometer, and same primary circuit is repeated in next experimental stage. This galvanometer section is secondary circuit, which at the time of balance show null deflection in this galvanometer at central zero position of indicator as balance condition, and this is tertiary circuit. In this tertiary circuit, across this 3 ohm resistance, the terminal P and Q have certain voltage, and that voltage is measured by primary circuit of potentiometer by a balance length of 40 cm or 0.4 meter. We have to find out corresponding balance length on potentiometer if voltage across this parallel combination of 4 ohm and 6 ohm is measured across Q and R point by this experimental setup. Let this primary circuit of potentiometer got a potential gradient X, and at the time of balance there is no current in this galvanometer. So this tertiary circuit physically connected with primary circuit for balance measurement, but electrically they are isolated as no current can pass from this circuit to potentiometer circuit or potentiometer circuit to this tertiary circuit, as at the time of balance galvanometer and this AP section has zero current. So let current in this tertiary section is capital I. So across 3 ohm when capital I current is flowing at the time of balance, it will have a voltage 3I across P and Q points, and it get balanced on 0.4 meter length. So with potential gradient X, this 3I is equal to 0.4x in this first experiment, and similarly 4 and 6 ohm in parallel are equivalent to a single resistance 2.4 ohm, and the same I current of 3 ohm passes through this parallel combination produce a voltage 2.4I, and voltage across Q and R is measured by the same primary circuit of potentiometer with potential gradient X with L length, and we have to determine this balance length. Now if the two relations are divided from each other, we will find that 3I when divided by 2.4I will cancel the current I in tertiary circuit, and similarly the balance length and potential gradient product of first experiment and second experiment when divides together, they will cancel the potential gradient. So without knowing potential gradient in primary circuit and current in tertiary circuit, we can compare the two resistances with balance length we have to find out second experimental balance length for 2.4 ohm measurement. So when this section is simplified, then L become product of 0.4 and 2.4 and divided by 3, and simplification will result in 0.32 meter length. So this parallel combination of 4 ohm and 6 ohm will balance on this AB wire length at 32 centimeter length. These two balance length, 40 centimeter in first experiment and 32 centimeter in second experiment, are corresponding to resistance used in tertiary circuit, 3 ohm in first case and 2.4 ohm in second case. So 3 ohm has a proportional balance length 40 centimeter and 2.4 have corresponding balance length 32 centimeter. Two important performance parameters of potentiometer are sensitivity and range. Sensitivity is ability of potentiometer to determine small potential difference during measurement, and we know potentiometer measure unknown voltage by comparison, and balance length gives the value of unknown voltage, and by normal scale measurement the minimum measurable length is 1 millimeter of wire length. So the voltage which come across 1 millimeter of wire length can be measured by a potentiometer, and if that value is small enough, we say potentiometer is capable of measuring small voltage. Now the voltage coming across unit length is called as potential gradient, and smaller the potential gradient, higher would be called as sensitivity, and we say sensitivity S is inverse of potential gradient. Now one can increase sensitivity by decreasing potential gradient, and potential gradient is product of potentiometer wire current and resistance per unit length. So potential gradient can be decreased by decreasing this product, and this product of current and per unit length resistance can be decreased by decreasing either current in primary circuit, by increasing rheostat resistance, or decreasing source voltage, or we can also reduce potential gradient by reduction in per unit length wire resistance by using thicker wire for potentiometer wire. So lower the potential gradient, higher the ability of potentiometer to measure smaller voltage. Now the maximum voltage which a potentiometer can measure across its complete AB length is known as a range. Now when we increase sensitivity by decreasing potential gradient with the same wire length, our range of potentiometer measurement will definitely reduce. If one want a higher sensitive measurement as well as better range in potentiometer, he has to increase the length of potentiometer wire, or he has to use better designed potentiometer having both sensitivity and range. The most important application of potentiometer from examination point of view is determination of internal resistance of a cell. We know that a cell or battery is a combination of source of EMF and a series internal resistance, and when this cell is connected to external load resistance capital R, we can measure the circuit current and terminal voltage, but we can't measure EMF or internal resistance from direct measurement, as both E and R comes in a combination. But in the circuit, we know that EMF act across both internal resistance and external resistance. So cell current in terms of EMF is given by this yellow highlighted relation. Now the voltage across load resistance at terminal is known as terminal voltage capital V, and capital V divided by load resistance could be another relation of current. And the most important relation to find out internal resistance of cell is the voltage which occur across internal resistance when cell is supplying current is difference of EMF and terminal voltage, and this E minus V voltage across internal resistance produce same current in this series circuit. Now this comparison relation of terminal voltage across external resistance and the difference of EMF and terminal voltage across internal resistance can relate external resistance and internal resistance, or we can say internal resistance is voltage across internal resistance, that is difference of EMF and terminal voltage divided by circuit current, and circuit current is terminal voltage divided by load resistance, and if we know EMF, terminal voltage and load resistance, we can find out internal resistance of cell. To measure internal resistance of a given cell by potentiometer, a primary circuit of potentiometer is formed by source voltage, current limiting rheostat resistance, and AB wire length having R ohm resistance for L meter length. A galvanometer is used to sense balance zero current condition by center null deflection position, and EMF source with positive end connected to positive potential terminal of AB wire, that is A. Primary and secondary circuit are connected together and suitable jockey position is obtained to get zero current or null deflection in galvanometer. And in this condition, as there is no current flow in this internal resistance, so there won't be any voltage drop in internal resistance. Physically, this internal resistance is present in this secondary loop, but since there is no current in this secondary loop at the time of balance, the voltage of AJ length of AB wire and EMF of source are equal and opposite in local loop. So the net difference of two produce zero current. In zero current condition, there is no voltage drop in internal resistance and true EMF get balanced across L1 length of potentiometer, and if potentiometer got potential gradient X as voltage per unit length, then L1 length has a voltage XL1 and that become equal to cell EMF. So we got first balance length L1 reading corresponding to EMF of source. Now for second reading, this key is closed and this place external known resistance in cell circuit and a tertiary closed circuit is formed as shown in this blue frame. And in this tertiary circuit, source EMF and completion of circuit circulate current in the circuit, and magnitude of that current depends upon value of source EMF and sum total of two internal and external resistance. Now the flow of current in this tertiary circuit also cause voltage drop in internal resistance, and due to voltage drop in internal resistance, the voltage available across terminal of the cell get reduced. This reduced terminal voltage of cell get balanced on potentiometer wire at new length L2. As terminal voltage is less than EMF, so this new balance length L2 is less than previous balance length corresponding to EMF. And we know for a cell, the voltage across internal resistance is difference of EMF and terminal voltage when current I is flowing in cell circuit, and current I of this tertiary circuit or internal resistance of cell is the same as at the time of balance. There is no current in this secondary galvanometer section, and current of tertiary circuit is terminal voltage divided by known resistance, and we know EMF is corresponding to L1 balance length XL1, terminal voltage is corresponding to L2 length XL2, and in a ratio calculation potential gradient will get cancelled out. So even when we won't know potential gradient, we can compare known external resistance with internal resistance of cell with this relation, and if we know two balance length and external resistance, we can determine internal resistance. These two numericals will explain theoretical concept of determination of internal resistance of a cell by potentiometer. In this problem, a cell of internal resistance 1 ohm is balanced on potentiometer wire without external load resistance at 6 meter length. We have to determine the suitable value of external resistance such that when the tertiary circuit has flow of current and that current produce some voltage drop in internal resistance, then reduced terminal voltage of cell balance at 4 meter length of potentiometer. So let the potential gradient on potentiometer is X. So voltage on unit length is X. In first case, without current, when potentiometer measure cell voltage by null deflection without any voltage drop in internal resistance, the true EMF balance at 6 meter length. So EMF becomes 6 times potential gradient. In the next case, when external resistance is connected to cell circuit, a current flow in tertiary circuit takes place and that will produce some voltage drop in internal resistance, and terminal voltage get reduced from EMF and reduced terminal voltage balance at 4 meter length. So per unit length got potential gradient X voltage. So 4 meter will have 4x voltage. So terminal voltage is 4x. We know that current is terminal voltage divided by external resistance and E minus V divided by internal resistance. Here terminal voltage is 4 meter balance length voltage 4x and EMF is 6 meter balance length voltage 6x, and internal resistance is given 1 ohm and external resistance we have to determine. And when we compare this current relation of external resistance and internal resistance, then this potential gradient will cancel out in ratio calculation and cross multiplication will fetch 4 equal to 2R, and calculation results as external resistance equal to 2 ohm value. So external resistance and internal resistance are compared by voltage of external resistance and voltage of internal resistance. In this example, a cell of EMF E balance at 2 meter length of potentiometer wire without connection of external resistance. Now the balance length of the same cell reduced to 1.8 meter when an external resistance of 10 ohm is connected across cell, and we have to determine internal resistance of cell. Let the primary circuit of potentiometer got potential gradient small x, and in first case when cell get balanced on potentiometer wire, there is no current in secondary galvanometer and cell circuit, so there is no voltage drop in internal resistance, and true EMF get balanced at 2 meter length. Unit length got x value of voltage, so 2 meter length got EMF 2x. And in the second case, when known 10 ohm resistance is connected in cell circuit, a tertiary circuit is formed which has a current in it, and due to that current flow, voltage drop in internal resistance takes place and cell terminal voltage get reduced, and the reduced terminal voltage balance at 1.8 meter on a potentiometer wire of potential gradient x, then terminal voltage is 1.8x. Now we can compare internal resistance and external resistance by this equivalent circuit model and current flow relation. For external resistance, the voltage across it is capital V, and for internal resistance during current flow, the voltage across internal resistance is E minus V. So current flow relation of external resistance and internal resistance can compare the value of internal resistance with external resistance. Here terminal voltage is 1.8x and EMF is 2x. External resistance is known to us, given 10 ohm. So the comparison of internal resistance with 10 ohm external resistance got this relation, and in this comparison relation, the potential gradient of two sides get cancel out. So without the knowledge of potential gradient, we can compare internal resistance with external resistance, and cross multiplication will result as 1.8 times R equal to 0.2 times 10 or 2, and simplification results as internal resistance is 2 divided by 1.8, or it is 10 by 9 or 1.11 ohm. This beautiful informative learning video has ensured your exam success, and you can solve both theoretical and numerical question based on application of potentiometer, as you know how two EMFs are compared by potentiometer and how potentiometer is used to find out internal resistance of a cell. Our other learning video of class 12th physics playlist are equally useful. You can use them in your study and can share them with your friends. If you need our online doubt removal classes or dedicated exam centering notes, do join our membership by pressing join button just beneath. Happy learning. Have nice time. Thank you.